Now let us consider the relation between the derivative and the property of the function being increasing or decreasing. We have seen already the proof of the theorem that if the derivative exists and is finite and is positive in some interval, then in this interval the function is increasing. The proof is an application of the mean value theorem we have discussed in some earlier section. Let me illustrate this. For example, the function fx equal to x is defined and continuous in all r, and the derivative is equal to 1, which is positive, and this is in good agreement with the fact that the function is indeed increasing. This is not changed if we multiply the function by some positive constant. Say fx plus 2x. So derivative is still positive, function is still decreasing in interval r. This does not change if we add some value. So we can conclude that a function y is ax plus b, where a is positive, is increasing. If a is negative, the function is decreasing, and if a is 0, the function is constant. What is important is that this property should hold in some interval. Interval is an important term. In particular, it means there are no holes, no missing points. Interval is a continuum, everything between two values. As a counterexample, consider the function fx is minus 1 over x. 1 over x looks like that, and minus 1 over x looks like that. If we consider the derivative, then we have minus x2 minus 1, which is minus minus, which is plus, x2 minus 2, which is 1 over x2. The condition is x must be different from 0. But now you see the derivative is positive in the whole domain for all x in the domain of definition, which is the union of two open intervals. So one might conclude that if the derivative is positive in df, the function might be increasing in df. Is it indeed? No, it is not. If you take two values, x1, x2, with different sides, that means on different sides of the 0, here the function value is positive, and here the result is negative. It goes down. So this is not an increasing function if increasing the argument results in lower function value. The function is not increasing in df. Why? This is true for all x in the domain of definition, but there is a hole. 0 is missing. It is not true that the derivative is positive in the interval from minus infinity to infinity. So in this large set, the function is not increasing. Only when we specialize in some small interval not containing 0. Say, if you consider just positive numbers, then this is already an interval. The function has positive derivative in this interval, so the function is increasing in this interval. Okay. Or if you consider all the negative numbers, or a subset of that, Once again, the derivative is positive in this interval, and indeed the function is increasing in this interval. So an important observation, if the function is increasing in two intervals, it is not sure, it is not automatic that the function is increasing in the union. No. Sometimes yes, sometimes no. But still, we can generalize this theorem. We can release this condition a little. Namely, imagine a function, say fx is equal to x for positive x or negative, and equal to 2x for x is less than 0. So it is x for positive x and 2x for x less than 0. The derivative is positive here, but no derivative at 0. And still, the function is increasing in R. So we can say that the function is increasing if in some interval, if the derivative is positive in some interval, or perhaps if it fails to be positive at one single point. It fails to be positive at this point because it does not exist. But then we must ask one more condition for the function f. Because if the function looks like that, it is positive here, but not increasing in this interval. So, well, let's say the function is equal to this value and this does not belong there. And this is what it's saying x value. We don't want these cuts, these jumps. So we must give one more condition. F is continuous. F is continuous in some interval, and derivative is positive in some interval up to one single point. Then the function is still increasing. Well, and if one single point does not matter, then we can afford to exclude 2, 3, 4, a finite number of points. So a slight generalization of this theorem looks like this. If the function is continuous, this is important now, in some interval, and the derivative is positive up to a finite number of points, that means it is positive at every x in R up to a finite number of points, then the function is still increasing. It may fail to be positive in two ways. First, the derivative does not exist, or the derivative exists but fails to be positive because it is 0. A nice example is a function y is x cubed. Then the derivative is 3x squared, which is positive everywhere up to one point, 0. It is not positive at 0. And still, the function is perfectly increasing for any set in R and in R alone, in entire R as well, even though it fails to be positive at 0. But the function is continuous. Well, honestly speaking, the function must be continuous is a sufficient condition, not a necessary one. Because you can have a function that looks like that. So it may happen that in some cases the continuity is not true and still the function is increasing. So this is a sufficient condition along with this one, but not necessary. And one more important remark is that we say a function is increasing in some set if higher arguments give higher results, and the function is decreasing in some set. We don't talk about a function being increasing at a point, but in some set containing at least 2 points. Then a strange situation may occur. Consider the function y is x squared. It looks like that. This function is increasing in the interval 0 infinity, and this function is decreasing in the interval minus infinity 0. Someone might be surprised that 0 belongs to both sets. We don't say that the function is increasing in this interval means it is increasing at each point. No, this is not a point property. This is a property in some set containing at least 2 points. We can even say that the function is strictly increasing. That means not decreasing. So 0 belongs to both of them, and this is not a problem, this is not a conflict. The function is indeed increasing in this interval, and it is indeed decreasing in this one. Well, it is easy to see from a graph, and it goes well even with the derivative. The derivative being 2x, which is you see this is positive for positive arguments, and this is 0 at 0. But as we have seen, 1 point is not 1 point when the function fails to be the derivative fails to be positive is not a problem. Yes, so that was how the property increasing and decreasing is related to the sign of the derivative.